Okay, hi, so welcome to this video on enzymatic reactions. Now in this video we're going to have a look at one example of an experiment where we can investigate how a condition, in this case pH, affects the rate of an enzymatic reaction. Alright, now let's jump straight in. The reaction that we're going to be looking at is the breakdown of starch, starch being a large carbohydrate, specifically a glucose store, right down into maltose. Alright, and then maltose eventually can be converted into glucose. That is actually how plants store their glucose. Right, this is an enzymatic reaction. The enzyme which carries out this reaction is amylase. Right, so amylase catalyzes the breakdown of starch into maltose. Now, what we're going to look at is how we actually investigate the effect of pH on this reaction. Right, so the effect, oh, that's just terrible writing, effect of pH on rate of reaction. Right, that is actually what we're going to be measuring. Now, you should already know. If you don't, then please have a look at my previous video on enzymes before you carry on with this video. You should know that the pH of wherever it is the enzyme is affects how the enzyme works, right? Enzymes can denature at pHs which are too far away from their optimum. Okay, so at a specific pH, its optimum, the enzyme will work the best, and therefore the rate of reaction will be the fastest. Okay, as you move away from that pH, the rate of reaction is going to slow down because the enzyme is not at its optimum, it's not working its best. Alright, now let's dive straight into the experiment. So what will we be using? So here you can probably tell which parts I've drawn and which parts someone else has drawn. So what we have here is a Bunsen burner. Okay, there's your Bunsen burner. This is your tripod. Okay, and on top you have this mat carrying a beaker. And this is a beaker full of water. Okay, water. And then we obviously have a test tube inside here. Right, let's get rid of these arrows because you should know what they are. Now, what we do is we heat our water to 35 degrees Celsius. Alright, so you heat the water to 35 degrees Celsius and you try as best you can to keep the water at 35 degrees Celsius. Okay, if you have access to the equipment, you can use a water bath instead, which is actually better, right? A water bath, you can set the temperature and it will just heat the water to that temperature. And then you can put your test tube in that water bath. But a Bunsen burner will work, it just isn't as good. Alright, and now what you're going to do is you're going to add amylase solution and buffer solution with a specific pH to the test tube. Right, the volume you're going to use is going to be small. It's probably going to be around about 1 centimeter cubed. Right, but you're going to add amylase and buffer into the test tube. Now, the buffer solution is what keeps your overall solution at a specific pH. Okay, and so basically we're going to repeat this experiment with different pHs. Okay, but let's say, for example, we use pH 6 in this case. Yeah? Then when we come to repeat, we're going to use different pHs. Okay, now before the experiment is fully carried out, we also use this, which is a spotting tile, right? A spotting tile. Now what we do is we add iodine solution to all of these wells. Now iodine is an orangey browny colour, so it'll look like this. There we are. Now all of those are full of iodine. I say full of iodine, you only need a very small volume. But yeah, all of those wells have iodine in them. Now this is the important part. If we go back up to here, okay, our test tube currently contains amylase and buffer, right? But it doesn't contain any of our starch that we want to break down. And this is what we do. Then we add starch solution, okay? So we add around 5 centimeter cubed of starch solution to the test tube. Okay, the way you're adding all of these, by the way, is via a pipette. Okay, so I'll say using a pipette. And then immediately start, sorry, you won't be able to see this very well, a timer. Okay, I'll just move it slightly so we can see it. Boom. Okay, so then you immediately start a timer. Reason being, because your reaction's happening. Okay, so as soon as you add your starch solution, your reaction should be happening, right? Your amylase should be breaking down your starch. Okay, and now what you do is you increment time. Okay, so 30 seconds is a good block of time to use. Okay, so at constant time increments, we add some of our solution to a well on the spotting tile. Okay, and so we add a very small amount. Okay, very small amount of our solution. So if we think inside here we go, let's say inside our test tube, right, we've got our solution. It's not going to be blue, by the way, I'm just doing it so you can see it. And so you've got your solution, etc., etc. Then we add some of this to our spotting tile, right? Every 30 seconds, it could be different time increments, it's down to you, right? Now what happens when starch is present, okay, iodine is actually the test for starch. And if starch is present, the iodine solution will turn blue-black, right? So very, very dark blue. I'm just going to draw it like this. So let's say we drop our starch in here. It goes this kind of color, right? It's actually a bit more black than this, but whatever, right? And so that tells you that you still have starch left. And if you still have starch left, then the reaction has not finished, okay? And so we keep adding it. Keep adding it. Next 30 seconds, right? So this is after a minute. It's still there. Then we add some more to this one. And it's still there, and some more, and another one, it's still there, right? So that means that after 30 seconds, 1 minute, 1 minute 30, 2 minutes, we still have starch present, which means the reaction has not finished. But then let's say, we add some of our solution after 2.5 minutes to this well, and it stays orangey brown, stays the color it already is. That means that there is no starch left, okay? The iodine has not caused the starch to turn the solution blue-black, and therefore our reaction has finished. And so we'd stop our timer and we'd say, there we go, reaction done. Okay, and then that would be great. We can mark down that time, and we are done. Now, what we would do then is we would repeat this entire process. Okay, repeat this entire process. Sorry, the screen is messing up here. There we go. We'd repeat the entire process at different pH values. Okay, we'd repeat everything. Oh, it is really messing up. There we go. We'd repeat everything at different pH values, and we'd see how long the reaction takes at each one, right? And then the fastest one, so when we achieve an orange color quickest, that would be our optimum pH. Okay, so that would be our optimum pH because that reaction has happened the fastest. Okay, just to summarize that experiment, what we do is we have water at around about 35 degrees Celsius, right? But we keep that temperature constant. It's very important because we need that to be a control variable, right? We add amylase solution and buffer solution to a test tube, right? So it's not mixed in with the water, it's in a test tube, okay? And we let that reach the temperature, and that's at a specific pH, okay? Then we add 5 centimeters cubed of starch solution to it, and then we immediately mix and start a timer, right? Before that's all happened, by the way, we've prepared a load of spotting tiles with iodine solution, okay? Because once we start the reaction, that's what we're going to add our solution to. So we've prepared this, and then at constant increments of time, so in this case 30 seconds, could be something else. If you wanted to be more precise, it could be 10 seconds, but you'd obviously need more spotting tiles. Then we add some of our solution and we see if there's a color change. If there's a color change, the reaction hasn't finished. As soon as we see no color change, so it stays brown, browny orange, then the reaction's finished and we stop the reaction, we mark down the time. And finally, we repeat this for different pHs. Okay, cool. So lastly, if we want to actually work out the rate of reaction, because it's all well and good saying it's faster, but the actual rate of reaction, okay, there is a handy formula to do that. So rate of reaction, okay, and the formula is 1000, okay, so I'm going to write actually rate equals 1000 divided by time taken, okay, and that is in seconds. Okay, so 1000 divided by time taken. Let's use our example up here. We said that it took 2.5 minutes, right? Well, 2.5 minutes in seconds is 150 seconds. And so in this case, our rate is equal to 1000 divided by 150, which gives us an answer of 6.7 if we're round, because it's 6.6 recurring, but that's 6.7 to two significant figures. Yep. Oh, sorry. I'll put it over here. Two significant figures. And the units for that are seconds to the minus 1. Okay, just because we've got a number, which is nothing, divided by seconds. So seconds to the minus 1 just means divided by seconds. Okay? And that will be how we calculate the rate for this specific reaction. In other types of reactions, when we're not just measuring time, if we're measuring, let's say, the amount of grams that are given off, right? So a change in mass, then rather than just per second, it would be grams per second, right? If we were measuring the amount the concentration changed, then that would be something like moles per decimeter cubed per second, right? So if you're measuring change of something, it is that something per second or per time. If you're dealing with minutes, then it'd be per minute. Normally you're dealing with seconds. Okay, so that's the difference in terms of rate of reaction on some other type of reaction. For this one, when you're just measuring time, you do 1000 divided by the time, and the units are seconds to the minus 1. All right, I'm going to stop there. I hope that did make sense. If you're still confused, please feel free to post a comment in the box below or send me a direct email using the link and I will get back to you. But as usual, please like and subscribe because it really helps me out. And of course, you'll be notified when any new videos become available. But thank you very much for watching and I look forward to seeing you in the next one.